our speaker today is Udisha. So she's currently a master in computer systems and engineering in Northeastern University. Traveled all the way from Boston for us today. Thanks for her being here. So she has worked as an intern data scientist in Schneider Electric, and her title of the talk today is Adopting Open Source Tools in Time Series Forecasting. So I will give the floor to Udisha. All yours.
Thank you. Hi everyone. Thanks for having me here today. My name is Udisha Chowdhury, and today I'll be talking about adopting open source tools for time series forecasting. So the slides for this talk is available in my schedule, so there's a link to my GitHub repo there. So to follow this talk, I kindly request you all to keep the slides open. So there, yes, due to some hiccups, we couldn't present it here today, but yeah. So I'll get started. With the talk, right? So as the demand for accurate forecasting increases across various industries, to be able to have powerful forecasting tools becomes even more crucial. Data scientists now have a wide array of libraries to choose from. Each of these libraries offer unique features and workflows in forecasting processes. Today in my talk, I'll be talking about a three-dimensional framework that all data scientists can use to evaluate forecasting tools before they apply it to their forecasting pipelines. We'll be focusing on two important open source tools, which are SKTime and SKForecast, and we'll be evaluating these two tools across this three-dimensional framework that's there. This is joint work with Murthy, who is a senior principal data scientist at Schneider Electric, as well as a lecturer at Northeastern University. Before we move on, I'd like to take a moment to introduce myself. I'm Udisha Chowdhury, and I'm currently a master's student at Northeastern University, majoring in computer systems engineering. I also work as a teaching assistant for the course Machine Learning for IoT Systems at Northeastern University. I most recently interned at Schneider Electric, which is a French multinational company known for its expertise in energy management and automation solutions. So as part of their AI hub, I worked on applying machine learning tools to IoT and time series data. I worked on benchmarking their internal machine learning library tool against open source alternatives like SKTime and SKForecast. So today I'll be sharing the valuable insights that I got from that experience. Before my master's, I also worked at Deloitte USA, first as an intern and then as a solution delivery analyst. I completed my undergrad in electronics and communication engineering from PS University. So this is the outline of the talk today. First, I'll be giving you all a foundational introduction to time series forecasting, the framework that it comprises of, the common stages that typically a forecasting project needs to go through. So this will better help us understand the context of where and how these open source tools fit into the forecasting pipeline. Then we'll look at the open source ecosystem that's available to us. So data scientists now have a wide array of libraries to choose from to perform forecasting. And it's very important to understand the options that are available to us. Mainly, I'll be focusing on how SKTime and SKForecast has gained growing popularity in the recent years. Then we'll dive into the main part of this talk, which is the three critical aspects for evaluating any forecasting tool, which is data understanding, data preparation, and backtesting. Then finally, I'll wrap up with some key takeaways, showing how using these open source tools really helps us minimize the boilerplate code. And also we draw a parallel between how SKTime and SKForecast has worked across these three critical aspects. So let's start with time series forecasting, right? So time series forecasting is all about predicting the future based on historical pattern. And forecasting models have seen a great evolution in the past few years. And this has been more evident by looking at the milestones in the M competitions. So these M competitions, they stand as a gold standard for evaluating forecasting tools. So when you look at the milestones in the end competitions, you can see that what started with basic statistical methods have now been dominated with purely machine learning techniques and ensemble methods. So this shift in the forecasting landscape tells us how important forecasting has become across various industries, right? Be it IoT, healthcare, forecasting in retails, right? So in each and every industry, forecasting is becoming really important. Now coming to the framework that it comprises of, okay, on the right side, you can see that there's a framework here. So I'll start with the past target variables. So the past target inputs are given to the forecasting model along with the exogenous variables. So let's clear the concept of the two of endogenous and exogenous variables here. So endogenous variables are the ones that are internal to the model. They are the variables whose future we are trying to predict, right? So they are endogenous variables. But in real world, time series data, they don't exist in isolation. There are always external factors that influence these predictions, right? For example, if you take retail's forecasting, your upcoming holidays or promotional events, they act like external factors that influence the prediction. And the other example would be energy usage forecasting. In that case, weather forecast would be a very good external factor that helps us predict its future, right? So the green box that you see here is the forecasting model. This is where all the magic happens. So it learns all the intricate relationships between the endogenous variables and the exogenous variables and makes predictions over the forecasting horizon. The forecasting horizon that you see on the upper right hand corner depicts how far into the future you want to predict. So that can be number of hours, number of weeks, or even number of years in terms of business planning, right? This is a basic framework for time series forecasting. Moving on, let's look at the common stages in any forecasting project, right? So this is given by a CRISP-DM workflow. CRISP-DM stands for Cross-Industry Standard Process for Data Mining, and it's a robust framework that all data science projects use, and even time series forecasting. So it comprises of 6 iterative phases, starting with business understanding. Business understanding is the stage where your definition should be very clear, your objective should be very clear of what you're trying to predict and why do you need it. So once that question and answer is set, the subsequent stages become easy to understand, right? So first is business understanding, then there's data understanding, where you explore your time series data, you capture the trends, the patterns, the seasonal components of time series data, which is very important even before you're applying forecasting, right? Then comes data preparation. So in real world, there is data which always comprises of some data quality issues, like there are always some missing values, some irregular timestamps. So the data preparation stage is where you are dealing with these data quality issues so that you're getting the data ready for it to be able to be applied to the forecasting model. Then comes the modeling stage, where you're applying your forecasting models based on what you learned from the previous stages. Based on what data characteristics that you have learned from the previous stages, you apply a forecasting model. Then comes the evaluation stage, which is backtesting. So backtesting is the reality check, right? It's where the rubber meets the road. You want to see how the forecasting model is actually working on historical value. To assess that, you need to evaluate your model. Then comes deployment, where you're actually able to give your predictions to the stakeholder to actually make business value. So these are the 6 iterative phases. Remember, these are iterative phases and not linear. That means you can go back and forth these stages based on what you want to refine, and if there are any changes in your project requirements, you can incorporate them. Moving on, looking at the open source ecosystem for time series forecasting, right? On this slide, there's SKTime, there's SKForecast, DARTS, Neural Prophet. So now these are these are some of the popular open source libraries that are there, and I want to highlight what are the advantages of these open source tools, right? First is that they're accessible and cost effective. They remove the barrier for entry. Organizations of all sizes, be it a startup or an enterprise, they have access to the same forecasting tools. Then flexibility and customizability, right? Like any other black box commercial tool, these forecasting tools are not like you. They're ones where you can modify the code based on your project requirements. So they're accessible, they're customizable in that sense, and community-driven innovation, right? So there are n number of contributors who daily contribute to these projects. That means that these bugs are getting fixed. There's more testing that's happening. So these open source tools are really community-driven innovations and integration with existing ecosystems. For example, SKTime and SKForecast, they seamlessly integrate with this scikit-learn framework, and Neural Profit integrates with PyTorch. So these are some of the advantages of using these open source tools. Now looking at the growing popularity of SKTime and SKForecast, on the slide that you can see some GitHub metrics, the number of stars that they have garnered, the developers watching their repo, the number of folks. So these are not just numbers, right? So they really tell us how vibrant the community is. So there are like n number of researchers, data scientists who are contributing to these projects. And whenever you're choosing a forecasting tool, you always want to have that assurance that this tool is going to be reliable and sustainable. And these numbers assure you that. Now coming to the main part of this talk, which is the 3 critical aspects for evaluating your forecasting models. So data understanding is the first critical aspect, right? Whenever you're choosing a forecasting tool, it should be able to provide you with EDA capabilities, which is exploratory data analysis, which helps you gain your basic data intuitions even before data preparation and modeling. So data understanding is a very critical aspect. Then comes data preparation, as discussed in the stages as well. Data in real world always comprises of these common data quality issues like missing values, nans, irregular timestamps. So whenever you're choosing a forecasting model, these models should be able to provide functions that help you pre-process your data. Then backtesting. Backtesting is a reality check. So it should be able to give these different validation strategies for you to test your model on the historical data. So these are the 3 critical aspects, and what we'll be doing today is looking at how SKTime and SKForecast help us with these critical aspects. And to make this conversation more tangible, I'll be using an energy usage forecasting problem as a running example throughout this talk. So this is the data that I'm talking about. It's the PJM hourly energy consumption data. So a little bit about this data set, right? So PJM is an independent non-profit organization that manages the electrical transmission over a greater part of the eastern United States. You can see the color-coded map area here. So PJM is responsible for the electrical transmission across these areas. So the data that we are using is coming directly from the PJM's website, and our power consumption is measured in megawatts. So we'll be focusing on using like 125 days worth of hourly data from this particular light company. Coming to the very first critical aspect, which is data understanding. Now let's see how SKTime offers its inbuilt capabilities to handle data understanding. So all the plots that you see in this slide are plotted using SKTime. So the first plot, which is plot series, right? So it's a simple line of code. It's used to just see your time series data. In our case, it's the power consumption model. You can see the train and the test split. It's a simple line of code. So in terms of power consumption, right, it gives you the range of power consumption. You can find out the troughs and the peaks, the peaks and the troughs, and so these are like the common intuitions that you can make from the data. Then coming to plot lags. Plot lags is again an important feature of SKTime. So plot lags give you help you understand the temporal dependencies of the data. So it's used to plot the time series and and the relationship between the time series data and its lag version. So if the plot is scattered, what does that mean, right? So it means that the time series data is not predictable and it's not highly autocorrelated. And if there's a proper like a diagonal pattern that you can see, that means that the time series data is highly autocorrelated. And so yeah, basically plot flags help us find out the temporal dependencies of the data. So these are the two strong functionalities that SKTime provide. Moving on, there's plot correlations, which is again a strong feature of SKTime. So that one line of code, right, it gives you these three plots, which is the original time series plot and the autocorrelation and the partial correlation plot. So why are these ACF and PACF plots important? So come to ACF, it helps us calculate the correlation between the time series data and its past observation. So the correlation is calculated based on all the past lagged values. So the correlation is cumulative. Whereas coming to PACF, it is the relationship between the time series data and a specific lag value. So it removes the intermediate lag effect. So these plots are very helpful in determining the order for AIMA models, right? So, for example, ACF plots are, so the order is determined by the ACF plot, that's for MA, and for PACF plot, the order is defined for AR model. So these are some examples where these plots can be helpful. So this was data understanding, and to sum it up, SKTime really helps us in this aspect. It's simple lines of code and helps us validate the actual intuitions of the data that we have. Coming to data preparation. So on this slide, you can see like the common data quality issues that we have. So first is the nominal data, where all the times series are consistent. Then there's missing data, which is represented by NaN value. Then there is irregular data, duplicate data. So these are common data quality issues that a data scientist needs to, take in. They need to handle them even before applying this data to the forecasting model. So when you're evaluating a forecasting library in this aspect, you need to be able to see how that library helps us analyze these data quality issues and mitigate them. So they should mitigate them through missing value imputation, detect outliers and be able to help remove them. Then there's detrending and seasonality adjustment, resampling irregular timestamps to fixed frequency, and time-based train and test splitting utility so that the temporal state of the data is maintained. Now looking at how SKTime helps us do this, right? So missing value imputation. So SKTime has this class called as imputer. So it's specially designed for time series data. Here the method that we've used to impute the missing values is mean, but you can have median, you can have a constant, you can do it using forward filling, backward filling. So in the snapshot you can see that there are two missing values in the first and the third hour, and those missing values are filled with some meaningful data. In this case, it's the mean of the non-missing values. Then coming to the second aspect, it's outlier detection and removal. So SKTime has this class called Hample filters, which is used to detect the outliers. So they have these two parameters, which is window length and n sigma. Window length is the parameter that is used to specify the rolling window length, and n sigma determines how sensitive this function should be in determining the outliers. So if you see the output of this function, right? So the blue line is the original time series plot, and the red spots that you can see are the outliers that are detected. There are more functions that SKTime offer, like detrending and seasonality adjustment. So most of these forecasting models assume that the data is stationary, and to achieve that, SKTime offers this class called detrender. It is used to remove the trend in the model. So if you see the output, the blue plot is the original training data, and the yellow plot is the one that has been detrended. So the trend has been removed, but make note of the fact that the seasonality and the pattern is still maintained. So the upward trend has been removed. So that's a very good feature of SKTime. And the most common, very basic one that comes very handy for all of us is SKTime offers this temporal train and test split function. It's just a simple line of code, and it easily helps us split the training and the testing data. Here you can see that 80% of the data is used for training and 20% is used for testing. So these are the various functions that SKTime offer in terms of data preparation. Coming to SKForecast, right? So SKForecast does not have any inbuilt capabilities to handle these data preparation features, but it works really well with pandas. So it expects the data scientist to know pandas library and it seamlessly integrates with it. So let's see how it does that, right? So coming to handling outliers using rolling statistics. So this line of code, you're calculating the mean and the standard deviation with the window length of 5 and the center is set to true so that the outliers are easily detected. Then there's resampling irregular timestamps. So the data that is resampled is resampled with the number of hours here. It can be months, days, depending on your needs. Then there's detrending using differentiation. So which is basically, again, some forecasting models want the data to be stationary. So detrending is used for that. And then handling missing data, right? Interpolation is another technique. Now coming to back testing, which is a very important feature here. So keeping the time in mind, let me go through quickly what back testing is all about. Okay. So let's go through this example here. So we are using the first 6 data points to create the initial model of the backtesting feature, right? So the first step in any backtesting process is to create an initial model. We are doing that using these first 6 data points here, and let's call it M. So you're fitting the model on this initial training data. Then you have to make predictions, right? Once the model is ready, you make predictions over the forecasting horizon. In this case, it's 7, 8, and 9 are the forecasting, are the target points. Remember that you already have the original data there, so you can always compute the performance metric. Then, now what do you do with this new data, right? Assume that you want to use this new data that's coming into your process. How do you process it? So then there are these 3 things that you can do to process this new data, which is to do nothing. You just use the initial training data to perform your backtesting, or you update the history using this model. So you just update this model using the new input that is there, or you retrain the entire model and create new forecasting parameters. So this is the iterative process, right? Once you process the new data, again you make predictions over the forecasting horizon. I would love to be able to show this with the animations here, but I hope you guys are following. So this is an iterative process. Now, look, what does the forecasting library offer here, right? So it should be able to fit any kind of model to do backtesting. It should be able to give these standardized implementations of forecasting metrics. So my development of a MAPE function should not be different than yours. So it should be standardized. So forecasting library should be able to offer that. Then it should offer different windowing features. Like how do you process the new data? Do you expand the initial training window or do you use sliding windows? So that is a different, that's the next feature. And then once you have decided to incorporate this new data, what do you do with it? Do you refit it or do you update it? So these are the different features the forecasting library offers. Now let's draw a parallel between how SKTime and SKForecast and how backtesting is performed in these, right? So first step is to declare a regressor. Here we are using a random forest regressor. These are the parameters. So SKTime uses this make reduction function to transform its time series data to a tabular function, and SKForecast does it using this forecaster auto regressor function. So once the models have been decided, you get into what you want to do with the new data, right? Which is, do you want to expand the initial training window or do you want to use sliding windows? So SKForecast offers these different kinds of window splitters to do that. For this example, we have used expanding window splitter. And if you draw a parallel with SKForecast and see the brown indication there, so expanding window is operated by this fixed train size parameter. If you set it to false, that means that in each and every iterative process of backtesting, the initial train size is increasing by the number of steps that's mentioned here. So So if you look at this, right, so SKForecast has like a compact backtesting function that's available, and SKTime offers various like validation techniques. And SKTime has, so the backtesting in SKTime is performed using this evaluate function. And it has these different parameters, the strategy, with clear definitions of refit and update, whereas in SKForecast, it has just one parameter, right? If you want to refit the model, you set the refit parameter as true, and if you want to update it, you set it as false. So these are the, this is the first step, that is setting up your backtesting parameters. And this is how you do it in SKTime and SKForecast. Now quickly looking at the results, SKTime's backtesting function is quite, like the output is quite detailed. So it actually gives you the error in each window, the training time for each window, the prediction for each window, the length for each window, and the cutoff for each window, and it actually gives you the training set, the testing set, and the predictions for each window, which is quite detailed. It's very informative to find out, like trends like window length versus prediction time, window length versus testing time, and all of that, right? Coming to SKForecast results, right? So there's this parameter, in the previous slides you can see, so there's this parameter called verbose. If you set the verbosity to high and set verbose to true, you can see the number of folds that, number of like, the training set and the testing data points that are there in each fold when the verbosity is set to true. And the backtesting forecaster function in SKForecast gives you the performance metric and the overall performance metric value and all the predicted values. So this is like this is how backtesting is performed in SKTime and SKForecast. Now looking at the results, right, in one slide for the same backtesting experiment, right? So here we had used window movement as expanding, the initial data as 240, the forecasting horizon is 24, window stride is 24, metric as MAPE, refit update as refit, window length is 24. So these are the some results that we can infer here. So if you look at the runtime, right, SKTime offers various validation strategies. There's some trade-off between the time that it's consuming, and SKForecast runs backtesting quite fast. It's a simple, compact function that's doing a backtesting, right? And these are some other results that you can infer from SKTime and SKForecast's backtesting result. Keeping the time in mind, I'll just leave you guys with one slide. So to conclude with, right, these open source tools really help us minimize the boilerplate code, help us accelerate development and minimize maintenance. If you use these open source tools, your lines of code are reduced by 85 to 90%, and your maintenance is also reduced by 45 to 50%. Right? You don't have to manually write. Imagine writing a code on backtesting on your own, right? It'd be like 100, more than that. Like you have to do make reduction, you have to do modeling, validation windows, and all of that. So that's a lot of lines of code. But if you use these open source tools, that it really helps you in your forecasting development. And to draw like a parallel between SKTime and SKForecast, right? So when it comes to data understanding, SKTime hooks into these stats models to provide visualization functions. Coming to data preparation, SKTime provides these various inbuilt utilities where SKForecast relies on pandas and backtesting. So despite the limited functionality of SKForecast, it's quite fast, but SKTime, since it's providing various validation strategies, it's taking more time, so there's some trade-off in its speed. Yeah, so this was the results that we gained from evaluating SKTime and SKForecast across this three-dimensional framework. I hope this talk really helped you guys make informed decisions in choosing your forecasting tools depending on your project requirements. Thank you once again. I'm open for questions, and yeah.
For being able to accommodate our technical issues today, really appreciate it. So right now we have 3 minutes for opening up the floor for questions. So
hey, so in my experience working with electric grid data, there's a lot of like different electric nodes, and you're actually going to produce forecasts for each node, and each node has their own time series distributed geographically. And I've found there's like, there's a lot of open source packages that takes a single time series and forecasts it out. And then there's like deep learning stuff you can make that kind of looks at the whole grid, but the history doesn't go back too far for deep learning. It's like 100 or a low thousands number of time series. So it was kind of like a gap in open source tooling around like having a lot of highly correlated, like kind of short time series. Do you know of anything that like approaches that problem?
So all of these evaluations that I've done have taken like, one single time series, and that's one of the pitfalls actually for using these open source tools. Yeah, I would say that developers are still working on it. If you see the SKTime's repo, they're fixing bugs. So yeah, they're still working on it, but I won't be able to give you an alternative from my experience. But I love to share with you if I have something in the future. Yeah. Thank you for the question.
Anyone else? We have one more chance.
So you mentioned for SKForecast, like you need to use pandas to do some of those
Yes,
processes. Is it possible, or is there any benefit to using SKTime for pre-processing and switching to SKForecast for forecasting? Is that helpful?
Yeah. So if you want to perform backtesting fast, then you have to use SKForecast. And if you want to do pre-processing using inbuilt functions of SKTime, then you have to use SKTime. So SKForecast works really well in backtesting. If you see that there's one compact function that does the backtesting for you. So yeah, that is again a good, like using one library for one aspect and using the other library for the other aspect is also option. Yeah, it's a great thing.
Okay, let's give another round of applause for the